All right, we're back with section 3.3, and I'm trying to clear these notifications. Okay, so section 3.3 is talking about parallel and perpendicular lines, and we have several theorems in this section. The first one is Theorem 3.9, which says if two lines are parallel to the same line, then they are parallel to each other. So I have a picture here of lines A, B, and C, and A and C are marked as parallel lines because they each have one arrowhead. And then lines B and C are also marked as parallel lines with the two arrowheads each here. So I kind of restated the theorem by just saying if A is parallel to C and B is parallel to C, then A must be parallel to B. So anytime we know that two lines are parallel to the same line, then they have to be parallel to each other. Okay, the next theorem is Theorem 3.10. This one says, in a plane, if two lines are perpendicular to the same line, then they are parallel to each other. So we have a picture of lines M and N, and each of those are marked perpendicular to line T with the right angle. So if those are both perpendicular to line T, then they also have to be parallel to each other. That's what this theorem says. Okay. We're going to see how we would go about proving that in the next slide. So remember, if we're proving a theorem, then we can't use that theorem, but we can use any of the other theorems we've had. So I'm given R is perpendicular to T, and S is perpendicular to T. We can see that on the diagram. There are also angles 1 and 2 that are marked, but there's nothing stated in the given statement for those. What I'm trying to prove is that R is parallel to S. So I'm trying to prove that if these two lines are perpendicular to the same line, T, then they must be parallel to each other. So the first thing that I would write in this statement if I was doing a two-column proof would be my given information. So I would say R is perpendicular to T. I keep wanting to say parallel. And S is perpendicular to T. And my reason for that would just be given. Now we could also do a paragraph proof or a flowchart proof. But the most often we're going to be doing these two-column proofs, so I'm just going to do it that way. Okay, so since I'm given that R is perpendicular to T and S is perpendicular to T, then I can also begin to look at angles 1 and 2 and figure out things that I can say about those, because clearly I need to use them if they're shown in the diagram, but nothing, even though nothing is said about them in the given statement. So if R is perpendicular to T, then that line where it intersects must have 90-degree angles on either side. So there's one that's marked here, but angle 1 is also could be marked with that same marking, and so it has to also be a 90-degree angle. So I can say that angle 1 and angle 2 are right angles, just by the definition of perpendicular. Oops, I don't have to write that here. Erase this. Okay, after that, if I'm thinking back to the theorems that we've used in the previous sections, I know that if I can show that angle 1 and angle 2 are congruent, then I can use the theorem that says that if two corresponding angles are congruent, then the lines have to be parallel. So the next thing that I want to be able to say is that angle 1 is congruent to angle 2. And the reason for that is that all right angles are congruent. They all have measure 90, and that's the definition of congruence, if their measures are the same. Okay, so since we've gotten to the point where we can say that angle 1 is congruent to angle 2, now I can say that R is parallel to S, because these two are corresponding angles. R and S are the parallel lines, T is the transversal. So this would be the converse of the corresponding angles postulate. Okay. All right, the next theorem, and I think this is the last one in this section, Theorem 311 says in a plane, if a line is perpendicular to one of two parallel lines, then it is also perpendicular to the other. So in other words, I have my lines L and M marked as parallel, so if these two lines are parallel and N is perpendicular to L, then it must also be perpendicular to M. So that's what this theorem is saying. Think about how we might prove that. If we know those lines are parallel, then we know corresponding angles have to be congruent, and which makes the one I marked in red have to be 90 just like the other was. And so that means that N is also perpendicular to M. So that's just thinking through it as kind of an idea of how we would prove it. So let's see how we might use some of these theorems. Here I have, from example 1, a miter box and a back saw are used to cut the frame for a painting at 45-degree angles. Explain why cutting the frame at this angle ensures that opposite sides of the frame will be parallel. So I kind of drew in with blue where the boards, what they would have looked like before they cut the angle off, and I'm sure my angles aren't exactly 45 degrees. But when they cut those off and they put the opposite direction angles together, they end up forming a corner like this. And since we want a frame to be a rectangle in this case, we want to have 90-degree angles at the corners. So if I put together two 45-degree angles, it will make a 90-degree angle. And so they would fit together well. If I had something like a 45-degree angle and a 35-degree angle, when I tried to put them together, I wouldn't be getting a 90-degree angle at the corner like I am here. All right, here's example 2. I'm given this picture on the right side here, and it says in a plane, A is perpendicular to B, C is perpendicular to B, and C is perpendicular to D. So everything's drawn in that's written in the given information. What I'm trying to prove is that A is perpendicular to D, so I want this to be true. So I extended the line A down so we can see where it would intersect. And we need to think about the things that we know and what we can conclude from those things. So I wrote down, this is a flow proof. I wanted you to see a different kind of proof. I wrote down the three things that are given on the left-hand side here, where I have A is perpendicular to B, C is perpendicular to B, and C is perpendicular to D. Those were given, so I just wrote given underneath, and I ran out of room here, so I wrote the given in the middle, but it's applying to both. So all these things were given to me. Now from the first two, A is perpendicular to B and C is perpendicular to B, I can conclude that A is perpendicular to C. I mean, not perpendicular, parallel, sorry. I keep mixing those words up today. So I have drawn lines from those two things on the left to show that using those two, I got to the point A is parallel to C. And underneath I wrote the reason, which was one of the theorems. If two lines are perpendicular to the same line, then they are parallel. I'm not given a name of a theorem because it's a number, and that doesn't help us very much, so I'm just writing down what the theorem says. And then finally, using the last part of the given information that I had, with A is parallel to C, I was able to conclude that A would be perpendicular to D as well. So if I have two lines that are parallel, and one of those lines is perpendicular to another line, then the other line of the parallel pair must be perpendicular to that D as well. So that was where I got this. So the theorem, stated in words and not with the number, says a line that is perpendicular to one of two parallel lines is perpendicular to the other. All right, one more example from this section. I have drawn in a rectangular prism, and this is going to be used just for us to. We noticed it in theorem, the last two theorems, 310 and 311. It began with in a plane. So the reason can be seen if we look at this figure. If I pick two lines, AC and BD, I can say that those are parallel. And also I can say that EC is perpendicular to AC. But because EC is not in the same plane as BD, it's not perpendicular to BD. So theorem 311 wouldn't work if they weren't in the same plane together. Now if I decided to use AB, which is in the same plane, it would work. So the theorem that says if two lines are parallel and one of those lines is perpendicular to another line, then the second line is perpendicular to it, that one only works when they're in a plane. And so that's what this picture is here, so that you can see the reasoning for those words. It doesn't work if they're not in a plane. Okay, so those were short, just a few theorems and a little bit of proofs, but you're going to be using those theorems in this section to look and see what you can conclude, and maybe to do a little bit of proof as well. All right, thanks, and let me know if you have any questions.